Lecture 13, Cloud Security Fundamentals. Theme, Cloud Security and Infrastructure Protection. Technical University of Moldova. Lecturer, Maxim Masiutin, Associate Professor. Introduction. Hello, everyone. Welcome to Lecture 13, where we dive into one of the most critical topics in modern cybersecurity, cloud security fundamentals. Over the next 2 hours, we will explore how organizations secure their cloud environments, the unique challenges cloud computing presents, and the frameworks and tools that help us protect data and applications in the cloud. Let me start with a question. How many of you have used a cloud service today? If you checked your email, watched a video, or collaborated on a document, you have already interacted with cloud infrastructure. The cloud is no longer the future. It is the present. According to recent industry reports from 2025, over 94% of enterprises now use cloud services in some form, and global cloud spending has exceeded $700 billion annually. But with this massive adoption comes equally massive security challenges. Data breaches in cloud environments have increased by 35% over the past 2 years. The 2024 and 2025 breach reports consistently show that misconfigured cloud resources remain the #1 cause of cloud security incidents. This lecture will give you the knowledge to understand and address these challenges. Part 1. Cloud Service Models, IaaS, PaaS, SaaS. Understanding the cloud stack. Before we can secure the cloud, we must understand what the cloud actually is. Cloud computing delivers computing services over the internet, providing on-demand access to resources without the need to own physical infrastructure. The National Institute of Standards and Technology, NIST, defines 3 primary service models: infrastructure as a service, platform as a service, and software as a service. Infrastructure as a service, IaaS. Let us start at the bottom of the stack with infrastructure as a service. IaaS provides virtualized computing resources over the internet. Think of it as renting raw computing power, storage, and networking. The cloud provider manages the physical data centers, servers, and network equipment. You, the customer, manage everything else: the operating systems, middleware, runtime environments, data, and applications. Examples of IaaS include Amazon Web Services EC2, Microsoft Azure Virtual Machines, and Google Compute Engine. When you spin up a virtual machine on AWS, you are using IaaS. You get a blank server with an operating system, and you are responsible for patching it, securing it, and managing everything that runs on it. From a security perspective, IaaS gives you the most control, but also the most responsibility. You must configure firewalls, manage access controls, encrypt data, and ensure your operating systems are patched. A common mistake organizations make is treating cloud VMs like physical servers in a data center. They forget that these VMs are accessible from the internet and often leave default configurations in place. Platform as a service, PaaS. Moving up the stack, we have platform as a service. PaaS provides a platform for developers to build, deploy, and manage applications without worrying about the underlying infrastructure. The cloud provider manages not just the physical infrastructure, but also the operating systems, middleware, and runtime environments. Examples include AWS Elastic Beanstalk, Azure App Service, Google App Engine, and Heroku. When a development team deploys an application to Azure App Service, they focus on their code. Azure handles server provisioning, load balancing, and platform updates. Security in PaaS is shared more heavily with the provider. You still secure your application code, your data, and your identity management, but the platform security is handled by the provider. However, this does not mean you can ignore security. Application-level vulnerabilities, insecure APIs, and improper access controls are still your responsibility. Software as a service, SaaS. At the top of the stack is software as a service. SaaS delivers complete applications over the internet. Users access software through a web browser without installing anything locally. The provider manages everything: infrastructure, platform, and application. You use SaaS every day: Microsoft 365, Google Workspace, Salesforce, Dropbox, Slack. When you compose an email in Gmail, Google manages the servers, the email application, and the security of the platform. From a security standpoint, SaaS appears to offload most responsibility to the provider. However, customers still manage critical aspects: user access, data classification, and configuration settings. Many SaaS breaches occur because organizations fail to properly configure their SaaS applications. They leave sharing settings too permissive, fail to enable multi-factor authentication, or grant excessive privileges to users. Part 2. The shared responsibility model. Defining responsibilities. Now that we understand the service models, we must discuss the most important concept in cloud security: the shared responsibility model. This model defines who is responsible for what in a cloud environment. Here is the fundamental principle. Security of the cloud is the provider's responsibility. Security in the cloud is your responsibility. The provider secures the infrastructure, the data centers, the hypervisors, and the network. You secure your data, your applications, your configurations, and your access controls. Responsibility distribution by service model. The distribution of responsibility varies by service model. In IaaS, the customer has the most responsibility. You manage operating systems, network controls, applications, identity management, and data encryption. The provider handles physical security, hypervisor security, and network infrastructure. In PaaS, the provider takes on more responsibility. They manage operating systems and runtime environments. You focus on applications, data, and access controls. In SaaS, the provider manages almost everything. Your responsibility narrows to data governance, user access, and application configuration. Common misunderstandings. Let me share a story that illustrates why this matters. In 2019, Capital One suffered a massive breach affecting over 100 million customers. The breach occurred because of a misconfigured web application firewall in their AWS environment. Capital One assumed AWS would handle all security, but AWS responsibility was limited to securing the underlying infrastructure. The misconfiguration was Capital One's responsibility under the shared model. The same pattern repeated in 2024 when several major healthcare organizations experienced breaches through misconfigured cloud storage buckets. These organizations had assumed their cloud providers would prevent unauthorized access to data. They were wrong. Configuring access controls is the customer's responsibility. Practical application. When you design cloud security, always ask, who is responsible for this security control? Document responsibilities explicitly. Create a responsibility matrix that maps every security function to either the provider, the customer, or both. Review this matrix regularly, especially when adopting new cloud services. Part 3. Cloud Security Alliance Guidelines. Introduction to CSA. The Cloud Security Alliance, or CSA, is a leading organization that defines best practices for cloud security. Founded in 2008, CSA has become the authoritative voice on cloud security standards and guidelines. Their work influences how organizations worldwide approach cloud security. The CSA Security Guidance. The CSA Security Guidance is their flagship document, now in its fourth major version. This comprehensive guide covers 14 domains of cloud security: cloud architecture and governance, risk management and compliance, legal issues, contracts and electronic discovery, compliance and audit management, information governance, management plane and business continuity, infrastructure security, virtualization and containers, incident response, application security, data security and encryption, identity, entitlement, and access management, security as a service, related technologies. Each domain provides detailed recommendations for securing cloud environments. I encourage you to read this document thoroughly. It is freely available on the CSA website. Cloud Controls Matrix. Another essential CSA resource is the Cloud Controls Matrix, or CCM. The CCM is a cybersecurity control framework specifically designed for cloud computing. It maps controls to major compliance frameworks including ISO 27001, NSD, PCI DSS, and GDPR. The CCM contains over 180 control objectives organized into 17 domains. Each control specifies whether the responsibility lies with the cloud provider, the customer, or both. This makes the CCM invaluable for assessing cloud security posture and ensuring compliance. CAIQ and STAR Registry. CSA also provides the Consensus Assessments Initiative Questionnaire, or CAIQ. This questionnaire helps organizations assess cloud provider security. It contains over 250 questions based on the CCM controls. The STAR Registry is a public database where cloud providers publish their security assessments based on the CAIQ. Before selecting a cloud provider, you should review their STAR certification. Major providers like AWS, Azure, and Google Cloud all maintain STAR certifications. Recent CSA initiatives. In 2024 and 2025, CSA has expanded its focus to address emerging challenges. They released guidance on AI security in cloud environments, zero-trust architectures for cloud, and quantum-safe cryptography preparation. The CSA Top Threats Report, updated annually, now highlights AI-related risks alongside traditional cloud security concerns like insecure interfaces, misconfiguration, and lack of visibility. Part 4. Identity and Access Management in Cloud Environments. The foundation of cloud security. Identity and Access Management, or IAM, is the foundation of cloud security. If attackers can compromise identities, they can access your data and systems without exploiting technical vulnerabilities. IAM answers two fundamental questions. Who are you, and what are you allowed to do? Cloud IAM Architecture. In cloud environments, IAM operates at multiple levels. First, there is the cloud provider's IAM system, AWS IAM, Azure Active Directory, Google Cloud IAM. These systems control access to cloud resources, who can create VMs, read storage buckets, or modify network configurations. Second, there is application-level IAM. Your applications running in the cloud have their own user directories and access controls. These may integrate with the cloud IAM or operate independently. Third, there is identity federation. Organizations connect their on-premises directories, like Active Directory, to cloud IAM systems. This enables single sign-on and centralized identity management across hybrid environments. Key IAM Principles. Least privilege is the most important IAM principle. Users and services should have only the minimum permissions required to perform their functions. In cloud environments, this means avoiding the use of root accounts, creating specific roles for specific tasks, and regularly reviewing and revoking unnecessary permissions. Just-in-time access is gaining adoption. Instead of granting permanent privileges, access is provided temporarily when needed. AWS has IAM Access Analyzer, Azure has Privileged Identity Management, and Google Cloud has IAM Recommender. These tools help identify and reduce excessive permissions. Service accounts require special attention. Many cloud breaches occur through compromised service accounts with excessive permissions. These accounts often have standing privileges, and their credentials are stored in code repositories or configuration files. Use managed identities whenever possible. AWS IAM roles, Azure Managed Identities, Google Cloud Service accounts with workload identity. Multi-factor authentication. Multi-factor authentication is non-negotiable in cloud environments. Every human user should authenticate with at least 2 factors. Cloud providers now offer passwordless authentication options using FIDO2 security keys or biometric authentication. For privileged accounts, administrators, DevOps engineers, security personnel, consider hardware security keys. Software-based MFA apps are vulnerable to phishing attacks. Hardware keys are not. Identity governance. Beyond technical controls, cloud IAM requires governance. Implement regular access reviews. Automate user provisioning and deprovisioning through identity lifecycle management. Monitor for anomalous authentication patterns using cloud-native tools or third-party security information and event management systems. The 2025 Verizon Data Breach Investigations report found that compromised credentials were involved in 44% of breaches. Strong IAM is not optional, it is essential. Part 5. Data encryption in transit and at rest. Why encryption matters. Let us talk about protecting data itself. Even if attackers breach your perimeter, encryption ensures they cannot read your sensitive information. In cloud environments, Encryption protects against multiple threat vectors, malicious insiders at the cloud provider, attackers who compromise adjacent tenants, and data exposure from misconfigured storage. Encryption at rest. Encryption at rest protects stored data. All major cloud providers offer encryption for storage services. AWS encrypts S3 buckets and EBS volumes using A.E.S-256. Azure Storage uses 256-bit AES encryption. Google Cloud encrypts all customer data at rest by default. But default encryption may not be sufficient. Default encryption often uses provider-managed keys, meaning the cloud provider controls the encryption keys. For sensitive data, consider customer-managed keys or bring your own key solutions. With customer-managed keys, you control the keys through cloud key management services like AWS KMS, Azure Key Vault, or Google Cloud KMS. You define key rotation policies, access controls, and audit logging. If you delete the key, the data becomes permanently inaccessible. Bring your own key, or BYOK, goes further. You generate keys outside the cloud and import them. Some organizations use hardware security modules in their data centers to generate and protect keys before uploading to Cloud KMS. Encryption in transit. Encryption in transit protects data moving across networks. Transport Layer Security, TLS, is the standard protocol. All communication between users and cloud services should use TLS 1.3, the latest version. Older versions, particularly TLS 1.0 and 1.1, have known vulnerabilities and should be disabled. Within cloud environments, encrypt internal traffic as well. Virtual private clouds should use encryption between services. AWS offers VPC encryption, Azure Virtual Network Encryption, and Google Cloud VPC service controls. Service mesh technologies like Istio and Linkerd provide mutual TLS between microservices. This ensures all service-to-service communication is encrypted and authenticated. Key management best practices. Key management is often harder than encryption itself. Follow these practices. Separate keys by sensitivity level. Do not use the same keys for development and production environments. Implement key rotation. Automated key rotation reduces the impact of key compromise. Cloud KMS services support automatic rotation. Enable it. Audit key usage. Monitor who accesses keys and when. Alert on anomalous access patterns. Plan for key recovery. If you lose access to encryption keys, you lose access to data. Implement secure key backup and recovery procedures. Consider envelope encryption for large data sets. Encrypt data with a data encryption key, then encrypt that key with a master key. This limits exposure and enables efficient key rotation. Part 6. Multi-cloud security and container security. The multi-cloud reality. Most organizations today use multiple cloud providers. A 2025 survey found that 87% of enterprises have a multi-cloud strategy. Organizations use AWS for compute, Azure for identity integration with Microsoft 365, and Google Cloud for machine learning workloads. Multi-cloud increases complexity significantly. Each provider has different security tools, different IAM models, and different networking architectures. Security teams must become proficient in all platforms. Multi-cloud security strategies. Adopt a cloud-agnostic security layer. Tools like HashiCorp Vault provide secrets management across all clouds. Security information and event management platforms aggregate logs from multiple cloud providers. Cloud Security Posture Management Tools, or CSPM, scan configurations across clouds. Standardize policies using policy as code. Open Policy Agent, or OPA, lets you define security policies that apply across clouds. Write policies once, enforce everywhere. Establish a common identity layer. Use an identity provider that federates to all clouds, Okta, Azure AD, or Ping Identity. Avoid creating separate identities in each cloud. Container security fundamentals. Containers have revolutionized application deployment. Docker containers package applications with their dependencies, ensuring consistent behavior across environments. But containers introduce new security challenges. Container image security is your first concern. Images may contain vulnerabilities inherited from base images. Always scan images before deployment. Tools like Trivy, Claire, and Anchor analyze container images for known vulnerabilities. Use minimal base images. Alpine Linux and distroless images have smaller attack surfaces than full operating system images. The fewer packages in your image, the fewer potential vulnerabilities. Never run containers as root. Configure containers to run as non-privileged users. Use read-only file systems where possible. Limit container capabilities using security contexts. Container registries need protection too. Use private registries with access controls. Enable content trust to ensure image integrity. Implement image signing with tools like Cosign or Notary. Kubernetes Security. Kubernetes orchestrates containers at scale, but its complexity creates security challenges. The Kubernetes attack surface includes the API server, data store, kubelet agents, and the container runtime. Secure the Kubernetes API server. Enable authentication. Never expose an unauthenticated API. Use role-based access control, RBAC, to limit what users and services can do. Enable audit logging to track API calls. Network policies control pod-to-pod communication. By default, all pods can communicate with all other pods. Implement network policies to restrict communication to only what is necessary. Pod security standards replace the deprecated pod security policies. These standards define 3 levels: privileged, baseline, and restricted. Use the restricted level for sensitive workloads. Secrets management in Kubernetes requires attention. Kubernetes secrets are base 64 encoded, not encrypted by default. Enable encryption at rest for ECT. Consider external secrets management with Vault or Cloud KMS integration. The 2025 Kubernetes security landscape includes several important tools. Falco provides runtime security monitoring. KubeArmor enforces security policies at the system level. OPA Gatekeeper enforces admission control policies. Part 7. Serverless Security and Infrastructure as Code Security. Serverless Computing Security. Serverless computing, also called functions as a service, abstracts away all infrastructure management. AWS Lambda, Azure Functions, and Google Cloud Functions let you run code without provisioning servers. The provider handles scaling, patching, and availability. From a security perspective, serverless shifts responsibilities significantly. You no longer manage operating systems or runtimes, the provider does. Your focus narrows to application code, function configuration, and data handling. But serverless introduces unique challenges. Functions are event-driven, triggered by HTTP requests, queue messages, or database changes. Each trigger point is a potential attack vector. Validate and sanitize all input, regardless of source. Function permissions require careful management. Each function needs an execution role with specific permissions. Apply least privilege rigorously. A function that reads from S3 should not have permissions to write to DynamoDB. Cold start security is an emerging concern. When a function has not run recently, it must initialize fresh. Attackers may try to time attacks during cold starts when initialization logic runs. Dependencies remain your responsibility. Serverless functions use libraries just like traditional applications. Scan dependencies for vulnerabilities. Use tools like SNYK, NPM Audit, or OWASP Dependency Check. Infrastructure as Code Security. Infrastructure as Code, or IAC, defines cloud resources in configuration files rather than manual console clicks. Terraform, AWS CloudFormation, Azure Resource Manager templates, and Pulumi are popular IAC tools. IAC improves security by enabling consistent, repeatable deployments. But it also creates new risks. Misconfigurations in IAC templates become misconfigurations in production infrastructure. Scan IAC templates before deployment. Tools like Checkov, TFSec, and KICS analyze templates for security issues. They detect overly permissive security groups, unencrypted storage, and missing logging configurations. Treat IAC as code with full software development lifecycle security. Store templates in version control. Require code review for changes. Implement automated testing in CI/CD pipelines. Secrets in IAC are a common vulnerability. Never hardcode credentials, API keys, or passwords and templates. Use secret references to external secret managers. Enable secret scanning in your repositories with tools like Git Leaks or Trufflehog. State file security matters for tools like Terraform. State files contain sensitive information about your infrastructure. Store state files securely. Use encrypted remote backends like S3 with Encryption or Terraform Cloud. Drift detection ensures deployed infrastructure matches your IAC definitions. Cloud resources can be modified outside of IAC through console changes or scripts. Detect and remediate drift to maintain security posture. Part 8. CNAPP, API Security, and Emerging Trends. Cloud-Native Application Protection Platforms. CNAPP, Cloud-Native Application Protection Platform, is a recent category that consolidates multiple cloud security capabilities. Gartner coined the term in 2021, and by 2025, CNAPP has become essential for organizations with significant cloud footprints. CNAPP combines several previously separate tools: cloud security posture management for configuration analysis, cloud workload protection for runtime security, cloud infrastructure entitlement management for permission analysis, and infrastructure as code scanning for development time security. The benefit of CNAPP is unified visibility. Instead of managing 5 different security tools with 5 different dashboards, CNAPP provides a single view of cloud security posture. This enables correlation of risks across the development and runtime environments. Leading CNAPP vendors include Palo Alto Prisma Cloud, Wiz, Orca Security, and Lacework. AWS, Azure, and Google also offer native CNAPP capabilities through their security services. When evaluating CNAPP solutions, consider coverage across your cloud providers, integration with your development pipelines, and the accuracy of risk prioritization. API Security. APIs are the connective tissue of cloud applications. Microservices communicate through APIs. Mobile apps called backend APIs. Third-party integrations use APIs. The 2025 threat landscape shows API attacks increasing dramatically. Over 60% of organizations experienced an API security incident in the past year. API security starts with authentication and authorization. Use strong authentication for all API calls. OAuth 2.0 and OpenID Connect are standard protocols. Implement proper authorization checks. Verify that authenticated users have permission to access requested resources. Rate limiting prevents abuse. Without rate limits, attackers can perform brute force attacks, denial of service, or data exfiltration through rapid API calls. Input validation applies to APIs just as it does to web applications. Validate all input parameters. Use schema validation with open API specifications. API discovery is challenging. Organizations often do not know all their APIs. Shadow APIs created by development teams without security review. API security tools can discover APIs through traffic analysis. API gateways provide centralized security controls. AWS API Gateway, Azure API Management, and Kong enforce authentication, rate limiting, and traffic analysis at the gateway layer. Monitor API traffic for anomalies. Baseline normal behavior and alert on deviations. Look for excessive data returned, unusual access patterns, or attempts to access undocumented endpoints. Emerging cloud security trends for 2025 to 2026. Let me conclude this section with emerging trends you should watch. Zero Trust architecture is no longer theoretical. It is the expectation. Cloud security increasingly assumes no implicit trust based on network location. Every access request is verified, regardless of source. AI security cuts both ways. AI tools help defenders analyze logs and detect threats, but attackers use AI to craft sophisticated attacks. Cloud-based AI services require their own security considerations around model protection, training data security, and inference endpoint security. Quantum computing preparation is beginning. While quantum computers cannot yet break current encryption, organizations are starting to inventory cryptographic usage and plan migrations to quantum-resistant algorithms. NSD standardized post-quantum cryptographic algorithms in 2024, and cloud providers are beginning to offer quantum-safe options. Confidential computing protects data during processing using hardware-based trusted execution environments. AMD SEV, Intel SGX, and ARM confidential compute architecture enable workloads where even the cloud provider cannot access data in use. FinOps and security are converging. Security teams work with finance teams to understand cloud costs. Since security controls affect spending and cost optimization must not compromise security. Part 9. Practical Lab Exercise Outline. Hands-on cloud security. To reinforce today's concepts, I want to outline a practical lab exercise you can complete on your own time using free-tier cloud accounts. Exercise 1. Create a secure S3 bucket configuration. Enable default encryption with a customer-managed KMS key. Configure bucket policy to deny unencrypted uploads. Enable access logging. Block public access. Exercise 2. Implement IAM least privilege. Create an IAM user with only the permissions needed to read objects from a specific S3 bucket. Use IAM Access Analyzer to verify no excessive permissions exist. Exercise 3. Scan a container image. Pull a public Docker image. Scan it with Trivy. Identify and document all critical and high-severity vulnerabilities. Exercise 4. Scan a Terraform template. Take a sample Terraform configuration that creates EC2 instances and security groups. Scan with sec or checkoff. Identify misconfigurations and remediate them. Exercise 5. Configure API Gateway Security. Create a simple API using AWS API Gateway. Add API Key Authentication. Configure rate limiting. Enable CloudWatch logging. These exercises provide hands-on experience with the concepts we discussed today. Conclusion. Let me summarize what we covered in today's lecture on cloud security fundamentals. We began by understanding the three cloud service models: IaaS, PaaS, and SaaS. Each model has different characteristics and different security implications. Knowing the model helps you understand your responsibilities. The shared responsibility model is the most critical concept in cloud security. The provider secures the infrastructure. You secure your data, applications, and configurations. Misunderstanding this division causes most cloud breaches. The Cloud Security Alliance provides essential guidance through their Security Guidance document, Cloud Controls Matrix, and Star Registry. These resources help you assess and improve your cloud security posture. Identity and access management is the foundation of cloud security. Implement least privilege, require multi-factor authentication, and govern access through regular reviews. Encryption protects data at rest and in transit. Use customer-managed keys for sensitive data. Implement TLS 1.3 for all network communication. Multi-cloud environments require cloud-agnostic security tools and standardized policies. Container security spans image scanning, runtime protection, and Kubernetes hardening. Serverless security focuses on function permissions and input validation. Infrastructure as code security means scanning templates before deployment and protecting state files. CNAPP consolidates cloud security capabilities into unified platforms. API security addresses the growing attack surface of modern applications. For your preparation, read the CSA Security Guidance version 4. Review your cloud provider's shared responsibility documentation. Practice the lab exercises I outlined. In our next lecture, we will explore infrastructure resilience, how to design systems that survive failures and attacks. Discussion questions. What are the most common misconceptions about the shared responsibility model, and how do they lead to security incidents? How should organizations approach security differently when operating in multi-cloud environments? What unique security challenges does serverless computing introduce compared to traditional infrastructure? Thank you for your attention. Are there any questions? Review questions. Explain the shared responsibility model and how security responsibilities differ between IaaS, PaaS, and SaaS. What is the Cloud Security Alliance, and what key resources does it provide for cloud security? Describe the principles of least privilege and separation of duties as applied to cloud IAM. Compare customer-managed keys and provider-managed keys for data encryption at rest. When would you use each? What are the key security considerations for multi-cloud environments? Explain the container security lifecycle from image scanning to runtime protection. What is CNAPP, and how does it consolidate cloud security capabilities? Describe the OWASP API Security Top 10 and explain why API security is critical in cloud environments. Key terms: API security, practices and tools for protecting application programming interfaces from unauthorized access and attacks. CSB, Cloud Access Security Broker, providing visibility and control for cloud applications. CCM, Cloud Controls Matrix, a CSA framework mapping cloud security controls. CNAPP, Cloud Native Application Protection Platform, consolidating cloud security tools. Container security, security measures for protecting containerized applications throughout their lifecycle. CSA, Cloud Security Alliance, the leading organization for cloud security guidance. CSPM, Cloud Security Posture Management, monitoring cloud configuration for security issues. CWPP, Cloud Workload Protection Platform, securing cloud workloads. Envelope encryption, a technique using a data encryption key wrapped by a master key, enabling efficient large-scale encryption. FedRAMP, Federal Risk and Authorization Management Program, a U.S. government cloud security certification. IaaS, Infrastructure as a Service, providing virtualized computing resources. IAM, Identity and Access Management, controlling who can access what in cloud environments. IAC, Infrastructure as Code, managing infrastructure through machine-readable configuration files. KMS, Key Management Service, cloud provider service for managing encryption keys. Kubernetes, an open-source container orchestration platform with security features, including RBAC and network policies. PaaS, Platform as a Service, providing a platform for developing and deploying applications. SaaS, Software as a Service, delivering applications over the Internet. Serverless security, security practices for function-as-a-service environments, focusing on permissions and input validation. STAR Registry, Security Trust Assurance and Risk, CSA's Registry of Cloud Provider Security Assessments. Shared Responsibility Model, the division of security duties between cloud provider and customer. References and further reading. Cloud Security Alliance, 2024. Security Guidance for Critical Areas of Focus in Cloud Computing version 4.0. NGSD Special Publication 800-144. Guidelines on Security and Privacy in Public Cloud Computing. NGSD Special Publication 800-210. General Access Control Guidance for Cloud Systems. AWS Shared Responsibility Model Documentation. Microsoft Azure Security Documentation. Google Cloud Security Best Practices. Kubernetes Security Documentation. OWASP API Security Top 10, 2023. CS Benchmarks for Cloud Platforms. Gartner Market Guide for CNAPP, 2025.